Imagine a world where computers can solve problems in seconds, problems that would take classical computers thousands of years. This is the promise of quantum computing. A mind-blowing leap in technology with the potential to revolutionize fields like medicine, material science, and artificial intelligence. But this revolution comes with a twist. This power could also be turned against us, threatening the very foundations of our digital world. At the heart of this enigma lies the bizarre world of quantum mechanics, a realm where particles can exist in multiple states at once. Quantum computers harness these strange laws to perform calculations in ways unimaginable for their classical counterparts. This is not just science fiction. Quantum computers are already here and they're getting more powerful every day. But are we ready for the consequences? One area that faces a significant threat from quantum computers is cryptocurrency, specifically Bitcoin. Bitcoin relies on complex cryptography for its security. Quantum computers could change the game. They have the potential to crack these codes. This could lead to the theft of vast sums of Bitcoin. The threat is not immediate, but it is real.
To understand the threat, we first need to understand the technology. What makes a quantum computer different from the computer on your desk? Classical computers use bits to store and process information. A bit can be either a 0 or a 1. Quantum computers use qubits. Qubits can be a 0, a 1, or both at the same time. This is due to the strange laws of quantum mechanics.
Think of it this way. A single bit can only be in one state at a time. It's like a coin that can only land on heads or tails. A qubit, however, can be in both states at once. It's like a spinning coin that hasn't landed yet. It has the potential to be both heads and tails. Now imagine having not one, but hundreds or even thousands of these qubits all working together. The number of possible states they can represent grows exponentially. This is where the true power of quantum computing lies, in the vastness of its computational space. This allows quantum computers to tackle problems that are completely intractable for classical computers. It's like the difference between trying to find a single grain of sand on a beach versus having the ability to sift through the entire beach at once. That's the kind of advantage we're talking about. Section 3. The Power of Superposition. Superposition isn't the only trick up a quantum computer's sleeve. Qubits can also be linked in entanglement. When qubits are entangled, they become interconnected. The state of one qubit instantly influences the other. This allows quantum computers to perform parallel computations. Section 4. Beyond the binary. Beyond the binary. It's important to note that quantum computers are not meant to replace classical computers entirely. Instead, they are seen as specialized tools that excel at solving specific types of problems. Problems that involve complex calculations and large datasets. The development of quantum computers is still in its early stages, but the progress being made is remarkable. Companies like Google, IBM, and Microsoft are investing heavily in quantum computing research. As quantum computers continue to evolve, they have the potential to revolutionize fields like medicine, materials science, artificial intelligence, and more. Their ability to analyze vast amounts of data and simulate complex systems could lead to breakthroughs in drug discovery, materials design, and our understanding of the universe itself. However, this incredible power also comes with risks. Risks that we need to understand and address before it's too late.
The year 2019 marked a turning point in the history of quantum computing. It was the year Google announced that its quantum computer, Sycamore, had achieved quantum supremacy.
But what does this mean? Quantum supremacy is the point at which a quantum computer can solve a problem that is practically impossible for any classical computer to solve in a reasonable time frame.
In Google's experiment, Sycamore performed a complex calculation in just 200 seconds. A calculation that would have taken the world's most powerful supercomputer at the time, Summit, an estimated 10,000 years to complete.
This was a watershed moment. It demonstrated the raw power of quantum computing and its potential to outperform classical computers in certain tasks by an astronomical margin.
Cracking the code, the Show 256 challenge.
The achievement of quantum supremacy sent shockwaves through the world of cryptography.
Why?
because many of our current encryption methods, including those used to secure Bitcoin, rely on the assumption that certain mathematical problems are too difficult for computers to solve.
This function takes any input and produces a unique 256-bit output, essentially a digital fingerprint. Bitcoin, in particular, uses a cryptographic hash function called SHA-256.
This fingerprint is what secures Bitcoin transactions.
The security of SHA-256 relies on the fact that it's computationally infeasible for a classical computer to find two different inputs that produce the same output.
This is what makes Bitcoin transactions tamper-proof.
Or at least it was.
The clock is ticking. While a classical computer would take billions of years to crack SHA-256, a sufficiently powerful quantum computer could theoretically do it in a matter of hours. This is because quantum computers excel at solving the types of mathematical problems that underpin many cryptographic algorithms. The threat to Bitcoin is not immediate. Quantum computers are still in their early stages of development, and it will likely be several years, if not a decade or more, before they pose a serious threat to SHA-256. However, the clock is ticking. The race is on to develop quantum-safe cryptographic algorithms. Algorithms that can withstand even the might of a quantum computer. If we fail to do so, the consequences for Bitcoin and the wider world of digital security could be catastrophic. The quantum sword of Damocles. The potential of quantum computers to disrupt Bitcoin's security is like a sword of Damocles hanging over the cryptocurrency world. It's a threat that looms large, even though it's not yet a present danger. The reason for this vulnerability lies in the very heart of how Bitcoin transactions are secured. Bitcoin uses a system called public key cryptography, where users have two keys, a public key and a private key. The public key, as the name suggests, can be shared with anyone. It's used to verify the sender of a transaction. The private key, however, is kept secret and is used to authorize the spending of Bitcoin. This system works because it's nearly impossible for a classical computer to derive the private key from the public key. This is where quantum computers come in.
Quantum computers are particularly adept at solving a specific type of mathematical problem known as factoring. Factoring involves finding the prime numbers that multiply together to make a larger number. It turns out that the security of many public key cryptography systems, including the one used by Bitcoin, relies on the difficulty of factoring large numbers. For classical computers, factoring large numbers is an incredibly time-consuming task. It would take them billions of years to factor the numbers used in Bitcoin's cryptography. Quantum computers, however, could potentially factor these numbers in a matter of hours or even minutes. This means that once quantum computers reach a certain level of power, they could potentially crack the public key cryptography used by Bitcoin and gain access to users' private keys.
The vulnerability of public key cryptography to quantum computers is not limited to Bitcoin. In fact, many other cryptocurrencies and even internet security protocols rely on similar mathematical principles. This means that the rise of quantum computing could have widespread implications for digital security as we know it.
If quantum computers were to fall into the wrong hands, they could be used to decrypt sensitive data, steal financial assets, and even disrupt critical infrastructure. This is not to say that the future is bleak. The cybersecurity community is well aware of the quantum threat and is actively working on developing quantum-safe cryptography.
The race is on to develop new cryptographic algorithms that are resistant to quantum attacks. These algorithms will be essential for securing our digital future in a world where quantum computers are commonplace.
It's important to remember that quantum computing is a double-edged sword. While it poses a significant threat to cybersecurity, it also has the potential to revolutionize many fields, including medicine, materials science, and artificial intelligence. The key is to harness the power of quantum computing for good, while mitigating its potential risks. This will require collaboration between researchers, policymakers, and industry leaders to ensure that quantum technology is developed and used responsibly.
The question is not if quantum computers will be able to break Bitcoin's security, but when. While estimates vary, many experts believe that we could see this happen within the next decade. This ticking clock has set off a race against time in the world of cryptography.
The challenge is to develop and deploy quantum-safe cryptographic algorithms before quantum computers become powerful enough to exploit the weaknesses of current systems. The task is daunting, but not insurmountable. Researchers around the world are already making significant progress in developing quantum-resistant cryptography.
These new algorithms are designed to be resistant to attacks from both classical and quantum computers. However, developing these algorithms is only half the battle. The other half is deploying them at scale. This will require a concerted effort from governments, industry, and the open source community.
The transition to a quantum-safe world will not be easy. It will require significant investment coordination and a willingness to embrace new technologies. However, the stakes are simply too high to ignore.
For Bitcoin and other cryptocurrencies, the threat is existential. If their underlying cryptography is compromised, their value and trustworthiness could evaporate overnight. But the implications extend far beyond the world of cryptocurrency.
A successful attack on public key cryptography could cripple online banking, e-commerce, and even national security systems. This is why it's crucial that we act now. We need to invest in quantum-safe cryptography research, develop standards and protocols for its deployment, and raise awareness about the quantum threat among policymakers and the public.
The transition to a quantum-safe world is not merely a technical challenge, it's also a challenge of trust. Quantum-resistant cryptography offers a path forward. By harnessing advanced mathematical concepts, we can create encryption methods resistant to quantum attacks. The future of trust will depend on our ability to adapt, innovate, and collaborate.
Quantum-resistant cryptography, a new hope. The threat posed by quantum computers is not inevitable. Quantum computers pave the way for new, robust cryptography. This is where quantum-resistant cryptography comes in. These algorithms are secure against both classical and quantum attacks. The goal is to secure our digital infrastructure for decades to come. The quest for unbreakable codes. Finding quantum-resistant algorithms is complex and ongoing. It's like searching for a needle in a haystack of mathematical possibilities. Researchers develop and test new algorithms for security and efficiency. We don't fully understand future quantum computers' capabilities.
The quantum revolution is upon us. Whether we harness its power for good or succumb to its potential for disruption is a choice we must make collectively. The future of Bitcoin, blockchain, and indeed the entire digital economy depends on our ability to adapt and innovate. We need to embrace the challenge of quantum-resistant cryptography, not with fear, but with the same spirit of exploration and ingenuity that has driven human progress for centuries. The path forward is clear. We need to invest in research, foster collaboration, and raise awareness about the quantum threat. By working together, we can ensure that the digital realm remains secure, trustworthy, and accessible to all. Let's embrace the quantum future, not with trepidation, but with the knowledge that we have the power to shape it for the better.